Hello, my name is Kevin McWilliams. This is the presentation that you were supposed to see on Tuesday, but since I'm an idiot, I am recording it this evening and I'm planning on uploading it to YouTube so that you guys can watch it and still be able to talk about it on Friday. We're going to break this lecture down into two different parts just so the file doesn't get too large to overwhelm YouTube. And so here we go. Here is the chemistry of killing. So the idea is that how can we use chemistry, or how have people used chemistry to kill other people? In some cases, how to kill lots and lots of people. Before we get into the specifics of this talk, we need to cover a few generalities. And so one of those generalities is shown here. So a lot of the chemicals that we'll talk about act really as poisons at high enough concentrations in the human body. Now, most of these occur due to some kind of interaction with a substrate. The easiest way to talk about this is the lock and key analogy, which is shown. So the lock in this case is being the enzyme or some kind of protein. The key then is a substrate, generally some kind of small molecule that wants to fit into that lock. So as you guys know, all locks are different. They all have their own little topology, and so the key has to fit that topology. So you can see on the right-hand side that the substrate, shown in purple, fits very nicely into the hollow area of the enzyme that has kind of that reverse topology, as it were. So this is very much akin to, say, your right hand fitting into a right-handed glove. They fit perfectly. It would not fit so well if you try to put your left hand into a right-handed glove. So we do have to be aware of at least the topology of these molecules and how they interact. The other thing that we have to consider is basically the grip. So the fit may be correct, but maybe that substrate doesn't actually stay in the enzyme for that long. In other cases, maybe the binding is so tight that it stays in the enzyme regardless of how long a time it is. It can't be taken out. So how we specify strength, at least as far as the interaction between differing molecules, is based really off of just electrostatics. So this is showing a representation of Coulomb's law. So Coulomb's law is the equation that you guys can see at the bottom of the screen. So this just, of course, is the idea that positively charged molecules would repel one another, negatively charged molecules would repel one another, but where you have a positive and a negative charge coming together, they will have an attraction. So on lots of these molecules, you'll want to look for where we have, say, oxygens or nitrogens or sulfurs. Anything in the upper right-hand corner of the periodic table generally is going to have a fairly large negative charge on it in a molecule due to its high electronegativity. Wherever you see carbons or hydrogens in a molecule, generally you're going to see that that's either normally some kind of partial positive charge, or maybe it doesn't really carry a charge at all. So what this is showing you is different types of strengths between two different molecules. So we have ion-dipole interactions where sodium is interacting with the negative oxygen on water. We have dipole-dipole interactions. You guys can see that methanol is interacting with chloroform. Both of those are polar molecules. And so these interactions really govern how tightly bound, say, the substrate is to the enzyme, and again, how strong or perhaps how weak it is bound. It also has very much to do with how the substrate interacts inside the body. So in general, things that are very, very nonpolar like to hide out in, say, the cell membrane, where it's also very nonpolar. If something is very, very charged or has lots of oxygens and nitrogens, generally those are soluble substrates, and they'll normally hang out, say, in the blood or in the serum, or possibly inside the cell in the cytoplasm, that kind of thing. So we're going to break this talk down into 4 separate areas: plant-based, animal-based, atomic-based, and then synthetic-based. So we're going to cut through the first section, plant-based and animal-based poisons. So starting off with the plants, you guys can see that we have poison oak, poison sumac, and poison ivy. Of course, almost everybody is susceptible to some kind of dermatitis caused by these. In general, it's a mirage if somebody says that they're not allergic to one of these 3. In general, that only is the case if they've only been exposed to it for a couple times. So in general, eventually you'll suffer dermatitis from these things as long as you come into exposure to it a few times or more. Of course, we're not talking about just dermatitis. That's not going to kill you unless you inhale it. Then that would actually be very bad. You never want to burn poison ivy or poison oak. You will kill yourself in that case if you try to inhale it. But we're going to talk mostly about things that are a bit more toxic than this. And so the plants that we're going to talk about certainly can kill you depending on the dosage. So the first one that we're going to talk about here is hemlock. And hemlock, as you can see, is kind of a pretty plant, has nice white flowers, grows to around 5 to 8 feet. There are two different sources of this, Conium maculatum, which is found in Europe, and then Conium carophyllioides, which is found in Africa. So in Europe, that's mostly around the Mediterranean, kind of a subtropical, still a little bit warm, and then in southern Africa as well. So hemlock is toxic. It contains many different alkaloids, and an alkaloid is something that really could be ascribed to a very general chemical. It's just something that's primarily consists of carbon, hydrogen, and nitrogen, with some of these other atoms coming into play, like oxygen, sulfur, the other ones that you guys can see there. So coniine is actually a very simplistic alkaloid. This is the structure shown here. We have a 6-membered ring with nitrogen, and then off the carbon, the alpha carbon next to the nitrogen, is this propyl group. Now here is a 3-dimensional. The blue ball shows the nitrogen, so this is a little bit better representation. This is what we would call the space filling model. So the LD50 for this compound, as far as when it's been applied to a mouse, you guys can see that we have this R- coniine and S+ coniine. What does that mean? And before we even get to that, in case you haven't learned about what LD50 is, LD50 is the lethal dose that would kill 50% of a population. So when we show these dosages for all these different compounds, understand that this would be to kill half of the population. A much lower dose technically would be ascribed a lethal dose, but of course that would kill a smaller proportion of the population. Okay, so back to this R- and S+ thing. What does that mean? So minus and plus refer to the handedness of a molecule. Just like your hands are non-superimposable, molecules can also be non-superimposable. And kind of the magic thing to have this occur is if you have a carbon that is bound to 4 different things. That's when you end up having this handedness associated with it. So you guys can see from the LD50 that depending on the handedness of coniine, whether it's right-handed or left-handed, you'll have 2 different LD50. So if you have a racemic mixture, which just means you have a 50-50 mixture of both R and S, you guys can see that it's 8 milligrams of coniine per kilogram body weight. So if we're talking about a normal kind of average human being, possibly that would be, let's say, 70 kilograms, 2.2 pounds per kilogram, so we're talking someone around 150 pounds. In that case, it would take approximately 150 milligrams to kill half of those people that weighed exactly 70 kilograms. So that's what that means. As far as the method of action, we're going to kind of see the same thing throughout the talk. So this is a neural cell. And you can see that it has a very large cell body, which then extends down these axons. So a neural cell is something that is able to transmit a signal. And how it does this is via chemicals. So this is a blown up version of the very end of an axon. And so the signal gets sent down the axon until it hits a terminus. Now the signal is, again, these neurotransmitter. The molecule that's shown there that has the positive nitrogen is called acetylcholine, and it's a very important neurotransmitter in the body. So you can see the nitrogen side of things is positively charged, where those red oxygens are would be slightly negatively charged. And of course, that has to do with where it's going to bind as well as the topology of that molecule. So the general thing is these neurotransmitters are contained within vesicles, which you can kind of think of as just little balloons. And when they get to the axon wall, they split open and they release these chemicals into what is called the synaptic cleft, which is just that dead space in between where the vesicle is popping open and then where the receptor site is. So it has to cross a very tiny distance. And so the receptor site is going to be what picks up the neurotransmitter and then keeps basically transmitting that signal. So the receptor site generally is part of a cell that then controls maybe the muscles, or maybe it controls how much pain that you feel, or maybe it controls your sense of warmth or coolness. So lots of different types, and it all depends on what the receptor site is. So this is a slightly more descriptive version. This is showing acetylcholine being produced and then being released into the synaptic cleft and binding to what is called a nicotinic acetylcholine receptor. What that means is that the receptor is sensitive to chemicals that are either nicotine-like in structure, or acetylcholine-like in structure. So, how conine works is it's going to basically block these receptors. It is referred to as an antagonist. What an antagonist is something that will bind to the same site that, say, acetylcholine wants to bind to, but it does not transmit the signal. And so it basically means that you'll continually have to have higher and higher concentrations of acetylcholine if you want to try and transmit that signal, because we're blocking so many of the receptors with the conine. So this is a blown up of the receptor site. You guys can see that ACH stands for acetylcholine, so you technically need two of them to open this type of membrane. So if we have conine there, we are going to block, and we're going to, again, prevent the transmission of these signals. As far as conine goes, interfering with these nicotinic acetylcholine receptors, it mostly affects the peripheral nervous system, and mostly on the somatic side of things, so muscle movement, muscle contractions. So in general, if you keep on sending a signal, that means that you're going to constrict the muscle. But if no signal is sent, then your muscles are generally going to be flaccid. So this actually results in paralysis when we block this receptor. And generally it sets in toward the bottom, down in the legs, and eventually it travels upwards until that paralysis sets in around the lungs. Of course, once that happens, you are DOA. You can't breathe and you get to die. So this is a picture showing flaccid paralysis of a mouse that was moving, then administered the drug, and now it cannot move no longer. It's basically just dead weight at that point. Cyanosis, so the bluing of the skin, is also another symptom of conine poisoning. And the most famous use of conine is the trial of Socrates, of course, the famous philosopher. In this case, he was on trial for basically not believing in the gods that the various cities believed in, as well as introducing new gods that the cities did not believe in. So he ended up being convicted by his fellow citizens, known as dicasts. They served as jurors, and he was sentenced to death by drinking a potion of hemlock. And we know that this is what killed him based on various accounts from people that were there. One of his proteges, which you've heard of, Plato, has an account of this event. And of course, not a very good way to die, since you very much notice it as you're dying. Unfortunately, it doesn't take out your brain first. So you're awake for that entire process of basically dying from asphyxiation. Good times. The next plant on our list is the castor oil plant. You can see it shown on the right there. Generally, it has some spiny green fruit. And contained within that spiny green fruit are seeds that look like ticks, and they're actually sometimes referred to as tick seeds because they have the kind of shape of a tick after it's sucked on some blood and filled up its sac after that. So the source of this is Ricinus communis, and it is generally found also in the Mediterranean area, so also a little bit of East Africa as well as in India. Many people also keep it as an ornamental plant, possibly not realizing the toxicity associated with it. So ricin is actually one of the more complex molecules that we're going to talk about this evening. You guys can see a picture of it on the right. Is actually made up of two different units, an alpha and beta unit. Overall, ricin is referred to as a lectin. And a lectin is just something that very much likes to bind to carbohydrates. So you guys can see how globular this thing looks on the left-hand side. The LD50 for humans in this case, depending on the method, is either 22 micrograms per kilogram for injection or inhalation. Or if you eat it, it would be 35 milligrams, and that's because you're able to destroy at least some of it as it passes through the gastrointestinal system. So you need a little bit higher concentration in that case. This is a focus on the alpha unit, and it is basically comprised of a bunch of alpha helices. And this is the most important part. This is going to be important as far as how this actually works to kill somebody. This is what would be called the active site of the alpha moiety. And so it's going to use this site. Other things will come into that site and actually ends up cleaving a bond, as we'll talk about in just a second. So how does this work? So it's called a lectin because it likes to bind to carbohydrates. So there are lots of carbohydrates hanging out on the cell membrane. And so they've found via studies that on a cellular basis, over 1 million ricin units can actually bind to a single cell. So just an enormous amount of ricin for any one cell. And this is just showing you a picture of all the different ways that something can be brought inside of the cell. So in general, the right-hand side is the easiest side, this clathrin pathway that basically makes a vesicle in reverse. So where we saw the neurotransmitter bursting into the synaptic cleft, we're making a vesicle and then taking it inside of the cell. But there are lots of different methods, whether it's clathrin dependent, whether it's not clathrin independent, or whether it's just maybe phagocytosis, where you have large particles that just get taken into the inside of the cell. So once ricin gets inside of the cell, it gets shipped around by the normal pathways, and eventually it's going to end up in the endoplasmic reticulum. And that's important because inside the reticulum is a protein, and the name of that protein is disulfide isomerase. And you can imagine that that breaks disulfide bonds. And so this is a close-up of the ricin molecule. And a disulfide bond is all that links the alpha chain to the beta chain. So this isomerase protein is going to come in here and cleave that disulfide bond and make it so that the alpha chain is offloading by itself. So really the beta chain is used only so that it gets inside of the cell. The alpha chain is where all the damage is done. So in general, the cell normally recognizes these types of proteins as being foreign, and it'll go through this ubiquitin proteasome process, wherein a bunch of ubiquitin molecules are placed onto this foreign substrate. And that basically makes it so that the cell recognizes that that's foreign and needs to be degraded by a proteasome. So how these generally work is ubiquitin looks for lysine that happens to be on the protein. And in general, once it latches onto the lysine, that kind of shuttles it toward being destroyed by the proteasome. Ricin is able to get around this because it doesn't really have a lot of lysine on that alpha structure, so it doesn't undergo this ubiquination process and therefore doesn't get destroyed by the cell. It actually interacts with a couple other proteins that are in the cell called heat shock proteins. And heat shock proteins are so called because they help change the conformation of proteins. So you guys understand that proteins sometimes get misfolded or the quaternary structure is not correct. So heat shock proteins try to help these out by putting some energy in and helping them refold themselves. So once that alpha moiety gets cleaved off from the beta unit, these heat shock proteins actually reform that alpha moiety until it becomes catalytic, and that just means that it's now in the correct form to start doing some damage. So the cell's actually actively hurting itself. So good job, cell. So once it's in its active form, it can undergo, using that active site that we were focused on earlier, in order to depurinate something. And what that means is that just means that we get to cleave off a purine. Well, what the hell's a purine? Well, purine is just a general term, again, normally associated with aromatic bases that contain nitrogen, which is the same thing that generally makes up DNA and RNA, such as guanine or adenine. These are purines. So specifically, this is going to come in, and it's going to start interrupting protein synthesis because it cleaves off a purine in the rRNA. and that becomes important during peptide formation. So that rRNA actually helps out with the translocation process. Basically, you guys can see where 3 and 4 there are attached to the mRNA, and as you go through the cycle, 4 moves into the place of 3. So what ricin does is it destroys this protein that helps out with that process so that no longer translocation is possible. You can no longer elongate the protein, therefore you can no longer synthesize protein. Of course, we constantly have to have a new protein being formed in order to keep living, so once that process is knocked out, again, you get to die. So some symptoms associated with this would be nausea, the flu, or running or high fever rather, coughing, vomiting, diarrhea, low blood pressure, and after a while, some seizures. Ricin lots of times gets confused for the flu because the symptoms are very similar, and that's the case with lots of these poisons that we'll talk about. Sometimes it's hard to identify them based on what the symptoms are. In some cases, you get confused for something completely different. So now we're going to talk about some ricin murders or attempted murders or just some weird things that occurred with ricin. So the most famous is the murder of Georgy Markov on September the 7th, 1978. So Georgy Markov was a Bulgarian dissident. So he grew up in Bulgaria and was on the radio and was also a writer and was very critical of the communist regime in Bulgaria at the time. So of course Bulgaria is very close to Russia. This was again one of the red countries that surrounded Russia. So it was communist at the time. So he felt he was endangered. Of course he didn't like living there. So he fled over to the United Kingdom and was living in London for a while. So on September 7th, he was crossing the Waterloo Bridge, which goes over the Thames River. And he ended up feeling a sharp pain in his back right thigh. And so he turned around and all he saw was some unnamed man that he did not recognize picking up an umbrella and hurriedly making his way to a taxi and then leaving. He didn't really think anything of it at the time. Possibly he was just bitten by something, who knows. But it turns out that he started feeling sick, and this is a picture of the umbrella. So after the fact, they thought that since he had mentioned the umbrella, that the umbrella was possibly the mechanism by which he was killed. So this is an umbrella gun. And so they think that a pellet was shot into his right thigh carrying the poison ricin. And that actually ended up being the case. When they were doing the autopsy, the coronaries found this pellet, very, very small, 1.7 millimeter in diameter. You guys can see there are 2 holes shown, and it was actually a kind of an X made with the bores. And so the ricin was filled into the pellet, and then the holes were actually covered with a sugar substance that, when came in contact with body temperature associated with that being inside of, say, a human being, would actually melt and move out of the way, allowing the ricin to go into the body. And so he ended up getting sick, checked himself into the hospital, got worse and worse and worse, and after about 3 days ended up dying on September 11th. He was shot on September 7th, which happens to be the birthday of Todor Zhykov, which was the Bulgarian leader at the time that he was making all these claims against the government, all the horrible things that they were doing. So they allegedly believe that this was a plot that was carried out in conjunction between the Bulgarian government, higher-ups therein, as well as KGB operatives. Speaking of the KGB, another example of an attempted murder in this case was on Boris Korczak. Boris Korczak was born in Poland, Lithuanian area, and was recruited by the CIA in 1973. The fact that he grew up in the Poland area means that he spoke numerous languages, Russia being one of the primary ones. And so he was an operative for the CIA who was able to infiltrate the KGB. He ended up getting exposed in 1979 and having to basically flee for his life as well as his family's life. And so he sought asylum in the US. The US, being such a nice government as we are, of course, denied his existence, denied that he ever worked for the CIA, and basically told him to go screw off. So he ended up having to go on various talk shows, television shows, to get the word out that, hey, he was an undercover agent, he'd been discovered by the KGB, he was on the run for his life, very fearful. Turns out in 1981, while he was in the town of Vienna, Virginia, which is very, very close to Washington, D.C., as he was shopping in a giant food store, he ended up feeling basically what he thought was a bite on his back. And he thought it was just a bee sting, but what he found later was that after months and months of kind of being sick, he finally passed what he thought was a kidney stone. And it turns out the kidney stone was a pellet very, very similar to the one that Markov had died from that contained ricin. So in this case, again, air gun of some kind of, basically something that was able to shoot a small pellet at a high velocity was implicated. What saved his life was the sugary substance that covered the holes that was supposed to basically melt away and allow the ricin to release, did not in his case, and so that's why he only got a little bit sick and actually did not end up dying. Another interesting case was Thomas Levy. So Thomas Levy in the early 90s was actually caught crossing the border with 130 grams of ricin, which you can imagine you could kill lots and lots of people or animals with that. His excuse was that he needed it for his farm in order to kill foxes and wolves and other predators from poaching his chickens. So the border that he was trying to cross was actually the American-Canadian border. He was in Alaska trying to get into Canada, and where his farm was located was actually all the way down in Arkansas. Interestingly enough, along with the 130 grams of ricin, he was also carrying a number of other things. He was carrying a shotgun as well as 3 rifles, 2 of which were .22, and 1 of which was a muzzle loader. He was also carrying a knife. He was carrying 20,000 rounds of ammo because that's necessary, as well as $89,000 in cash. So he actually didn't end up getting charged with anything initially and was initially let go, and of course they kept the ricin. Another incident was with the North American Militia in '97. So an ATF agent was able to infiltrate the group because they were suspected of terrorist activities, and lo and behold, 3 members were implicated in a terrorist plot. So home invasions of these 3 people resulted in a very, very large number of guns being discovered, as you can imagine, for the North American Militia. There was also a videotape that was discovered that had various explanations as far as ways to go about terrorizing, I suppose, as far as making bombs, various weaponry. One of the portions of the tape very much was like what you would see on the Food Channel, where it described in detail how to isolate ricin from a castor oil plant. And so they were convicted of terrorist activities and thrown in jail. The last one that we'll talk about as far as ricin goes involves the U.S. government and a Department of Transportation law, as it were. So an envelope was sent to a post office, and on the outside of the envelope it says, "Caution, ricin poison enclosed in sealed container, do not open without proper protection." So there's actually a warning on the outside of the letter. This was found in the post office in Greenville, South Carolina. Hey, what about that? So an award was put up of $100,000 for anybody that knew anything about who had sent this poison. You can see that there's a gloved hand, and inside that envelope was this little metal container that contained the ricin, along with a note, and it says that he is a fleet owner of a tanker company, and he does not want this new law to go into effect, which basically requires truckers to spend an additional 2 hours in the sleeper berth. So he didn't want to have to, I guess, pay for extra laziness. So this was signed Fallen Angel. Ricin was also subsequently later found in D.C. in the Dirksen Senate office building. Same type of deal, a note from Fallen Angel says, if you change the hours of service on January 4th, 2004, when the law was supposed to go into effect, I will turn D.C. into a ghost town. Obviously, he doesn't understand the way you turn DC into a ghost town is that you have a fight over the debt limit and then you just shut everything down. So that's how you turn it into a ghost town. So those are the ricin murders. Next on the list is strychnine. And so the tree on the left there is Strychnos nux vomica. And it has this nice orange fruit. Within that orange fruit are disc-like seeds. So where these are generally found, where strychnine plants are native to, are Southeast Asia, as well as Australia. And so the structure for strychnine, again, alkaloid, we're talking mostly carbon, hydrogen, nitrogen, and then some others. You can see that this structure is fairly complex, many rings. The globular structure is shown, the three-dimensional portrayal. The LD50 for strychnine, fairly low, 1 to 2 milligrams per kilogram for human. So again, typical 70 kilogram human will only take around 70 milligrams to kill half of the population. So how does strychnine work? So it's an antagonist for both glycine as well as acetylcholine receptors. So if we zoom in on the glycine receptor, so the molecule shown on the very bottom is again acetylcholine with that positively charged nitrogen. The other molecule that's shown on the bottom there is glycine. So again, those receptors are targeting those two molecules. So it affects the receptors for both of them. Again, antagonist means that it'll bind to the same spot, but it's not going to allow the signal to be transmitted. In this case, strychnine works on the glycine receptor and basically makes it so that it is always open. Or sorry, not always open, always closed, my bad. And that's a problem. So this glycine receptor allows the flow of chloride, which is a negatively charged ion. You guys saw earlier that acetylcholine was positively charged on the nitrogen. So in general, how you get a signal to occur is you reach an action potential, and an action potential is the result of having a large concentration gradient. So how this works is generally it blocks the glycine receptor, so it does not allow chloride to travel into the cell. And that's a problem because then it only takes smaller and smaller amounts of positively charged neurotransmitters in order to achieve an action potential. So it only takes very, very small amounts of, say, acetylcholine to start making your muscles constrict, much, much smaller amounts. This is just showing you the receptor. Again, generally they're comprised of 5 major subunits. Each subunit is generally comprised of a protein that has 4 helices that go through the membrane. So there are different types of receptors. And actually, humans, you all have different ones depending on what your relative biochemistry is. As far as the symptoms go, generally there's foaming of the mouth. Of course, with strychnine, there are convulsions. So this is showing somebody in the occiput position. They are convulsing and they are on their heels as well as on their occiput, which is the back of the head, and very painful. In general, of course, death results from asphyxiation. You're no longer able to breathe once it reaches the lungs. And so strychnine is an exceptionally painful way to die. So we'll talk first about some historical possibilities. This is a bust of Alexander the Great. He ended up falling ill out on the east side of his Macedonian Empire. Since where his empire was contained lots and lots of poisonous plants, it is up to debate whether he was poisoned by strychnine, belladonna, aconite, hemlock, or some other chemical, or possibly maybe he just fell down to ill health. But the thought is possibly that the reason that he died was because his wine was poisoned. But once he died, of course, his empire crumbled along with him. The next person on the list is this large lady on the right named Bella Gunness. She's also known as Lady Bluebeard. She was 6 foot, around 200 pounds, and was thought to have killed anywhere between 25 and 40 people. Her method of action was generally to marry somebody, then kill them and collect the inheritance money. So she did this several times until she had enough money where she bought a farm where she kind of resided permanently. She ended up dying, and when people were searching around her farm, what they discovered in the hog pen in the back were the remains of dozens upon dozens of people. And when testing was done on some of these corpses, they found very elevated levels of strychnine in their bodies. So just an exceptional serial killer in that regard. Most of it was done for money, but when you kill that many people, certainly that's a serial killer. This is Jane Stanford. Her last name, of course, implies the Stanford University over in California. Stanford University is really the result of her and her husband losing their only child, and so the thought was that their children would be the children of California as they made their way through Stanford University. She ended up being poisoned while in Hawaii, in Oahu, and that's where she died. She'd actually been poisoned before that in San Francisco, but noticed that there was something weird, that the water didn't taste quite right. It kind of had this bitter taste to it, and so she was able to induce vomiting, and so she lived. She only got sick for a little bit. But then when she ended up drinking some seltzer water while in Hawaii, she wasn't able to make herself vomit, and she ended up dying from strychnine. And some of her last words were, "This is a painful way to die." The thought was that possibly she was murdered by the president of the university, or possibly somebody on the board of trustees who do not see eye to eye with her as far as the direction of the university, but the case was never solved. This is a picture of Turgut Özal, who's the leader of Turkey, and he died in 1993. Initially, his death was put down to that of a heart attack, but his body ended up being exhumed and tested positive for elevated levels of strychnine as well as DDT pesticide. Either of which, of course, is not good for your body. This case has also not been solved, but now it's implicated that possibly foul play was afoot. So, some other specific cases. Thomas Neal Cream, who basically killed people between 1879 and 1892. So he grew up in Canada, studied medicine, and established a medical practice in the red light district in New York, offering illegal abortions. Several of his patients ended up dying. And he was actually sentenced in the U.S., but got off because the sentence was commuted by his brother, who pleaded for leniency. They also think that, of course, bribery was probably at hand. But since he was commuted, he was set free, and so he sailed to London and set up shop at 103 Lambeth Palace Road, and basically the same thing happened. He killed several other prostitutes and ended up being convicted. He was trying to frame other doctors for the crimes who were of much greater repute. And he also, based on talking with the police and others, knew way, way too much about the crimes themselves, and so he ended up being convicted. He was thought to be a sadist who just enjoyed punishing his victims. He has nothing on this guy. So this is a picture of Oscar de la Wanger, who is a horrible, horrible human being. So he was part of the Nazi Party, of course, and also was a member of the SS. And he really gained his renown by occupying Belarus during World War II and basically making sure that various towns were under Nazi control. And so this is a picture of what is called the Dirlewanger Brigade, and the brigade was made up of mostly criminals. And so his brigade was sometimes referred to as a penal brigade. And this is a picture of some of his brigade about to kill some poor people. So he was, to put it mildly, a lunatic, referred to by many of his peers as both a sadist, someone who enjoyed the pain of others, as well as a necrophiliac. Lots and lots of crimes. There was a rumor that he used to make soap by boiling horse meat with the bodies of dead Jews. And actually that's where strychnine comes into play. Jewish prisoners, normally women, were administered strychnine so that for he and his fellow officers viewing pleasures could watch them convulse to death. And generally while that happened, he also had them whipped. So Yeah. Lastly is Patsy Wright, who was the owner of a wax museum. So this is just a wax bust of Einstein as well as Jack Sparrow and Kim Kardashian. Now, which one is the real Kim Kardashian? Who knows? They're both pretty waxy. Which one of those two has the highest IQ? Also, who knows? So Patsy Wright was actually murdered by strychnine being put into her cough medicine that she was taking at the time. And again, this is an unsolved murder mystery, but the prime suspect was her ex-husband, who was up for charges for an arson trial, and the thought was that he killed her in order to make sure that she couldn't testify against him, but the murder was never solved. So those are some strychnine poisonings. Next on the list is belladonna. You guys can see the picture. This comes from Atropa belladonna. Nice big purple fruit. Belladonna takes its name from beautiful lady. Not that belladonna. There we go. Just a more in general beautiful lady. So where this is found is again Mediterranean area, subtropical. And the active ingredient in belladonna is atropine, which is again a handed molecule. So you can see there we have the left-handed and right-handed versions. The LD50 isn't quite as bad as some of the other ones we've talked about, 1 to 2 milligrams per kilogram. The reason that it's called belladonna, the plant was called belladonna, is because they used to use the atropine from the fruit. Women used to use this and would put it on their eyes and it would actually dilate the pupils, which generally meant heightened sexual prowess. In general, this was reacted with an acid, and so it would form a salt, and then that salt would easily dissolve in water. So that bottle is actually atropine sulfate. It had been reacted with sulfuric acid. So how does atropine work? Well, it's going to interact with a receptor. In this case, it's called a muscarinic acetylcholine receptor. That means the receptor is sensitive to both acetylcholine molecules as well as muscarine molecules. And I don't have a picture of muscarine up here because I suck, obviously. But how this works is for a receptor, of course, it's going to act as an antagonist as well. And so it's going to basically block these receptors. And that's going to be a problem because muscarinic receptors, there's 5 different types, M1, 3, and 5, and they mostly control the central nervous system, as well as the M2 controls the heart, and then M3 controls smooth muscle. So what this does is it basically blocks the parasympathetic division, as far as that's where mostly the muscarinic receptors are. And so you can see it constricts pupils, stimulates saliva production, slows heart, that kind of thing. So it's actually going to block that, which allows the sympathetic division to win out. So it's blocking the ability to constrict the pupil. That's why the pupil dilates. It doesn't allow the heart to slow, but it allows the sympathetic to win, so it speeds up the heart. So some symptoms associated with this are tachycardia. You just have this elevated heart rate coming out of nowhere. Blurred vision. Again, dilated pupils, just a very sense of confusion that results, high sensitivity to light, probably from having dilated pupils, and then also dizziness sets in. So some atropine poisonings. First one would be Cleopatra. So Cleopatra, of course, famous woman from the Egyptian Empire. Very, very beautiful, so reports go. Had dalliances both with Julius Caesar as well as Mark Antony. So Mark Antony is shown there. She ended up dying shortly after the Battle of Actium, where Mark Antony's fleet was basically destroyed. She was also there with her small fleet and ended up taking flight. Thought to have possibly killed herself by atropine poisoning, but actually this is still up for debate, of course, since so far back in history. Other accounts have her dying from the bites of an asp, and so possibly from snake venom. So inconclusive in that regard. Anna Buchanan was murdered by the man shown here, who was Dr. Robert Buchanan, who was her husband at the time. So Dr. Robert Buchanan actually divorced his first wife and then ended up getting married to a brothel proprietor. And so he actually was coming from Nova Scotia and coming across the border into the United States. And that's where he set up his practice. So once he divorced his wife and married the brothel owner, of course, many of his patients' friends did not approve of this. And so he planned to murder the brothel proprietor, collect the inheritance, and then remarry his first wife. And he thought he was going to be able to get away with this because he had witnessed a murder trial earlier where somebody had been murdered with morphine, with the giveaway being that the pupils of the victim were pinpricks. And so he actually didn't murder his wife with atropine. He murdered her with morphine and tried to cover it up, tried to make it so that the police didn't know that, by administering atropine to counteract the pinpoint pupils. And so the atropine was kind of used in this case as Schadenfreude, basically, to try and make it so that the coroners did not recognize the true method of death. But he ended up being found out and convicted. The last one on the list is Alexandra Gutter, who was poisoned by her husband, shown on the left there, Dr. Paula Gutter, who worked at Napier University in Edinburgh, UK. And so on the right is shown a picture of Napier University. So how he went about trying to do this was he went to the local Safeway, and his wife liked to drink gin and tonics. And so he poisoned a whole bunch of tonic water bottles and would put them back on the shelf. And the reason he did this was so that if his wife got sick and died, she wouldn't be the only one, and so it would be harder for people to basically track it back to him. Didn't work out that way. They still found out that he was the one that did it. His wife lived, and actually he's about, I think, to get out of jail soon. So maybe he'll be able to get back with his wife, or maybe not. Speaking of morphine, we have opium. So opium is our last plant on the list. It comes from Papaver somniferum. The somna kind of implies somnia, having to do with sleep. And really that's what opiates are good at, whether we're talking about morphine or codeine or hydrocodone, all these opiate derivatives. They're very much good as far as alleviating pain and making it easier to go to sleep, let's say. What we have pictures here are some of our United States soldiers walking through a poppy field, as well as a close-up of the poppy itself. So the massive amount of poppy morphine in the world is produced in Afghanistan. And actually the poppy crop has only increased since the United States has taken up residence in Afghanistan. Read into that whatever you like. So this is a molecule of morphine. You can see that it is also a ringed structure. It has these hydroxyl groups, these OH groups on the left-hand side. Our three-dimensional structure of morphine. Depending on how it's administered, it actually has several different LD50s. So the worst one would be intravenous, directly into the blood. Intraperitoneal, it just means that it's put in underneath your skin, so subcutaneous, let's say, and then oral, of course, is you're just taking it through the mouth. As far as the method of action goes, these are going to work on what are called opioid receptors. And these are located in the brain, neuronal cells. And so what this does is the morphine is going to basically block the receptor and no longer allow pain signals to be transmitted to the brain, which is the whole point of an opiate. So there are three different types of opioid receptors, delta, kappa, and mu. You can see that they all have the same typical alpha helice structure. And so specifically morphine likes to target the mu receptor, and so that allows for supraspinal and spinal analgesia, deadening of pain, so sedation. Also, if you're on morphine for a long time, you will become constipated. It does lead to addiction. So you'll hear all about morphine addicts or codeine addicts. There's also the sense of euphoria, which is very similar to that, which I associate with a happy, happy Pikachu. So some symptoms of morphine poisoning would be low blood pressure. Eventually, if you have enough morphine, you'll go into a deep sleep, a kind of coma-like state. And also, of course, the telltale pinpricks pricking of the eyes. So the most famous case of poisoning was from Dr. Harold Shipman, who was known as Dr. Death. Very notorious. So Dr. Death initially, before he was convicted for murder, he was actually had to go to rehab. He was addicted to pethidine, which has a very similar structure in a couple cases to that of morphine. He actually didn't use morphine per se to murder his victims. What he used instead was diamorphine, also known as heroin. So heroin is a much more powerful drug than morphine because you can convert those hydroxyl groups into acetate groups. And those acetate groups make it much easier for this molecule to cross the blood-brain barrier where the mu-opioid receptors are. And so it's very easy to get a larger concentration of the drug into the brain. So he was people were concerned about him anyway because he had such a high rate of fatality among his patients. It ended up that the very last person that he killed was how he was caught. So that is Kathleen Grundy, and she died after being administered a lethal dose of heroin. And he was caught primarily because he forged her last will, in which her entire estate was given over to her doctor. And so they were able to spot the forgery. He was implicated in her death. And when they searched his home, they found the belongings of many of his other victims. Apparently he was just stealing small amounts of jewelry and cash from them. So that was Dr. Death. He was convicted of 15 murders. Possibly the police think that that was an even higher number, but certainly 15. So that was all the plant-based poisons that we'll talk about, and then we'll now move into the animal-based ones. So we're not going to talk about all of the animals here, we're just going to focus on 3 different ones. The first being frogs in the family Dendrobatidae. So these are the poison dart frogs, as they are well known due to their very, very nice colorations. These guys are found in the Amazonian jungle, down in South America. And their toxin that they excrete is called batrachotoxin, which is Greek for frog poison. It's like the following structure here shown. So the LD50 for this is actually fairly low, 2 to 7 micrograms per kilogram, so it doesn't take a lot. So this is actually excreted by the frogs just on their skin. Of course, defense mechanism also can be used possibly on the offensive, but mostly for the frog it's a defensive mechanism. Interestingly enough, these poison dart frogs are no longer poisonous if you remove them from their native environment. So the idea is that they can't produce the alkaloid without having some kind of dietary supplement that gives them the precursor. So there's some kind of beetle that they're eating that has the alkaloid, which their body then metabolizes into this active batrachotoxin, which then gets excreted through their skin. So how this acts is it's a neurotoxin, and it's going to act on a sodium pump. So again, this is kind of the subunits that when they come together, they make a pore. And you guys can see on the lower right-hand corner that these kind of loops that are going into the middle there are called are selectivity filters. And so depending on those loops, that kind of dictates the size of the ion that can actually travel through the pore. So in this case, we're talking about sodium. Sodium is one of the smaller cations in your body. Potassium is, of course, larger. Calcium, and probably similar in size to sodium. So how this works is that you're going to have that batrachotoxin is going to bind to the receptor, and then it's basically going to allow sodium to cross through the membrane. And so in this case, it actually allows a signal to be sent, which opens the channel, and it binds so tightly that the channel then never closes, which is a problem. Again, we said that how these things work, how a signal is transmitted, is by having a concentration gradient, and that's what produces an action potential, which allows, say, a muscle to contract. So if we don't have a concentration gradient, we're no longer going to have an action potential, and so that's going to lead to paralysis. So this is a picture that's showing, of course, in general, normally you would have 3 sodium cations being pumped out and 2 potassium cations pumping course, that's to maintain the concentration gradient. So if that thing's open the entire time, you no longer have the gradient, and that's going to be a problem. So generally this leads to convulsions, shortness of breath, excessive saliva production. And where this was used, we don't really have specific cases, but certainly it's been used by South American tribes as far as both for hunting as well as for just killing animals. And so you can see that he is putting the poison on the tip of the dart. They then load that into the blowgun, and they can fire that thing fairly accurately. And again, it doesn't take much as far as the LD50 goes. So if it's a low enough dosage, you can just incapacitate someone. A high enough dosage, of course, you'll kill someone. This idea of having poison tip darts or poison tip arrows isn't a new one, certainly. It's been used throughout history by, say, the Gauls, the Romans, the Chinese, the Greeks, and even the Scythians. So a well-known form of warfare. Next on the list would be the pufferfish, the blowfish, the balloonfish, the bubblefish, or the globefish. It has all of these names. And I mean, it doesn't get much cuter than the picture on the left. I mean, look at that thing. It's adorable. So this comes from the family of fish called Tetraodontinae. And pufferfish are so named because of their ability to blow up. But really, they're nice small fish, and they're very highly maneuverable. However, if all else fails, of course, they can go into berserker mode, and certainly once that happens, nobody's going to want to try to ingest that. And also, on top of that, of course, they are highly poisonous. So where these things are found are generally in tropical waters around the globe. And the toxin is tetrodotoxin. You can see here it has just a ton of oxygens on this molecule. And not quite as bad as the frog poison, but still fairly low, 334 micrograms per kilogram to kill 50% of a mouse population. So how does this work? It's actually very similar to the frog poison. So that large colored picture on the right is supposed to indicate a sodium pump. And again, we're just showing the kind of close-up structure of these sodium pumps, how these things, these subunits come together to make a pore. The interesting thing about this one is that it specifically targets what are called fast sodium pumps. So there are fast sodium pumps and there are slow sodium pumps. So what tetrodotoxin does, instead of binding with a receptor which forces the channel to stay open, what it does is it just sits basically in the channel and blocks it. And so this means that your muscle is no longer going to be able to fire in that case. Because we can no longer, again, have a concentration gradient. So what this leads to is numbness of the mouth, again, excess salival production, headaches, excessive sweating, just an overall feeling of malaise, of being tired. And so some famous tetrodotoxin poisonings were the unsolved murder of David Hughes, who was actually an ex-paratrooper. And he comes from Northamptonshire of the United Kingdom. And so he was a decorated paratrooper, and once he got out of the military, he kind of became an entrepreneur, and what he wanted to do was to try to set up a biodiesel plant. So a biodiesel plant is just a plant that tries to convert biologically degradable products into an energy source. So if you've ever seen a large SUV, sometimes you'll see that those things can actually take biodiesel as a form of fuel. So he was trying to set one of these suckers up in Sierra Leone, and while he was down there, he either was intentionally poisoned, i.e. murdered, or possibly he just ordered a bad plate of pufferfish. But he ended up ingesting tetrodotoxin. It was found in his body after the coronary was done. After coroners had to look at his body. So they found elevated levels. And it's still unclear whether he was poisoned or murdered. Even the motive is unclear as to why he would have been murdered. So that was never solved. Another case was Edward Bachner, and he actually tried to purchase 98 milligrams of tetrodotoxin. Of course, this type of chemical is monitored very carefully. And so he was put on suspicion, and he was actually convicted of trying to kill his wife. because he had a life insurance policy on her for $20 million. So he had 20 million reasons to kill his wife. So those are a couple of tetrodotoxin poisonings. Technically this isn't an animal, technically this is a bacteria, but we're still putting in this classification. So this is a couple pictures of Bacillus anthracis. In the upper right-hand corner, you can see some cultures of this trying to be produced on some red agar. So what this bacteria produces is anthrax. And anthrax is an exotoxin, and all that means is that it excretes the toxin. So just like the frog excreted its toxin through its skin, bacteria excrete the toxin. And there's actually 3 of them. And of course the LD50 of this is variable. Since a bacteria can technically reproduce, it would only really take 1, so really there is no LD50 value. Interestingly enough, if you zoom in on the active site of the one in the middle there, we actually have more anthrax. So rock on, people. So how does this work? So we actually have 3, again, different proteins that are being excreted by the bacteria. And so one of them is the protective agent, that which allows it to get inside the cell. And the one is then the lethal agent, which really does most of the damage. So we have our 3 different types being excreted. And so this protective agent is going to bind to a receptor on the outside of the cell. The receptor is shown in red on the right-hand side there. The protective agent is shown in tan. And it's going to bind, and then a furin is going to come along and basically pop off one side of that protective agent protein. And this allows it to form a heptamer. A heptamer just means 7 things, in this case arranged in a cycle. So once this occurs, we'll have the other 2 toxins bind to that heptamer, and then that entire thing gets taken into the cell via endocytosis, one of these ways that a cell can bring things inside, like we talked about earlier. And so 2 things occur at this point. We end up having one of these toxins interact with calmodulin, and that basically converts ATP into cyclic AMP. And so ATP is what your body uses for a fuel source, and so this is going to chew up a bunch of that and make it into cyclic AMP, and that's a problem. You're going to kind of run low on energy. The other problem is that it interferes with this mitogen activated protein kinase, the acronym MAPKK. And basically, once it inhibits this protein and basically makes it so that it can no longer function, the cell believes that it's supposed to undergo apostasis. And that's just a fancy word for programming a cell death, where the cell basically disintegrates into a very bunch of small vesicles and no longer is able to work. You can imagine that's problematic and eventually will lead to death. So depending on how you get anthrax, you may or may not live, so it's best if it's just the subcutaneous form. It'll just make a sore as shown, very disgusting sore, but eventually most people will survive that type of anthrax. If you happen to inhale or ingest it, though, it gets much, much worse, and so you'll have feelings of nausea, vomiting, again, running a high fever. You also end up having bloody diarrhea. Again, coughing. And so the most famous case of as far as anthrax goes would be the 2001 anthrax attacks. So these actually occurred, if you can remember back then, right after the terrorist attack on the Trade Center buildings on September 11th. And so this was about a week after that. They found various letters at either postal services or places where mail was sorted. And these letters were being sent to various media centers as well as a couple different senators. So the 3 letters here, the one on the left is being sent to Senator Daschle, the one in the middle is being sent to Tom Brokaw, and the one on the right is being sent to the editor of the New York Post. Various claims about death to America, death to the infidels, Allah's great type of thing, trying to implicate possibly Islamic entities as far as having symbiote anthrax. So again, a reward was put up at $2.5 million. And these anthrax spores were actually found all over the place: Kansas City, Missouri, Indianapolis, New York City, Princeton, Washington, D.C. So they never made it to their possibly intended targets. Again, most of the mail, if it's being sent to somebody higher up, gets sorted first by somebody that's not as well paid. And so 5 people ended up dying from this. 17 others ended up being infected. And again, this was never solved. They think that a biochemist working for the government who had access to anthrax, Bruce Ivins, was the culprit. But we'll never know, due possibly toward his guilt or possibly just due to the intense pressure being put on him by the U.S. government. Dr. Ivins committed suicide, so probably no answers will be forthcoming as far as who was actually behind the anthrax attack. So that's where we're going to cut off this portion of the talk. The second portion then will be based off of elemental poisons, as well as synthetic-based poisons. So click over to part 2. And